So previously we had worked out the exponential regression, and we had set out the relationship of, we took the natural logarithm of GDP and we regressed it onto a constant, and then the growth rate by time, where we're estimating G and time being the independent variable. In the regression, if we look at the regression we ran, it's clear that the dependent variable, blue, was given by the natural logarithms of GDP. We regressed it onto, is there a constant? Yes, true, there was a constant, and the constant is this value here, which is an estimation, it's a regression estimation of the initial seed value for the GDP, the natural logarithm GDP series, and the 0.08 is the estimation here of growth, where we can take the growth rate, the G, as being the quarterly growth rate of GDP over the entire period 1947 all the way through to 2015. Okay. So the coefficient estimates that we have here from the LinEst regression give us the 7.65 is equivalent to the initial value for GDP, the natural logarithm of GDP, and so an estimate of this value, and this 0.008 is an estimate of the exponential growth rate, exponential quarterly growth rate. Underneath we have standard errors and R squared. So this is the typical LinEst output that you get when running a LinEst estimation. The growth rate estimated here of 0.008 per quarter represents the growth rate for the entire period between 1947 and 2015. But from a policymaker stance, when we think of from the implementation of the Taylor rule, this growth rate is something that's not known in advance. So if we're in 1949, we don't actually know the growth rate for the entire period 1947 to 2015. And if we were to set out a real-time estimate of growth, we would have to look at each period, each time period retrospectively. We couldn't, so from the perspective of 1950, 0.008 is an ex-ante measure, but policymakers only have ex-post measures of growth. So to get a real-time measure of growth, and this is something that a number of economists have emphasized, so we could think of work by economists such as Orphanides, who considered Orphanides real-time measures monetary policy. And For instance, he has pointed out in recent years simple policy rules have received attention as a means to a more transparent, effective monetary policy. Often, however, the analysis is based on unrealistic assumptions about the timeliness of data availability. This permits rule specifications that are not operational and ignore difficulties associated with data revisions. He goes on to say, I demonstrate that real-time policy recommendations differ considerably from those obtained with Expost revised. And then further says, I showed that estimated policy reaction functions obtained using Expost revised data can yield misleading description of historical policy. So although the raw data that we have here is obviously revised, we can still look at the effect of the trend. The trend changes through time, and that's something that probably we need to capture when estimating a Taylor rule, that the actual growth rate over time varies. So 0.008 is for the entire period, but then historically that would have changed. And policymakers at any given point in time, let's say looking in 1952 back, might have experienced higher levels of growth. So the trend, the historical trend, ex-post trend is important. And we'll try to capture that by using a rolling regression in the next worksheet. So this spreadsheet will entitle Regression, and I'll put first, and then the second, copy everything here and bring into the next spreadsheet. We'll take this to one side, and now we will rerun the regression. So let's take out what we have here. Just delete. And I will run the regression. Rather a series of rolling regressions. So linest, one more time. I can write that in. Linest equal to linest. And our y values will start from here. So this is the dependent variable. I'll dollarize the first term just to lock the cell reference. Then I take the second series, which is, so I'm regressing the independent variable, which is time. And again, I'll dollarize the first observation in the series of time. So dollarize the 1, that means that cell reference will be locked. And do we want the constant? Yes, we do. And do we want the other statistics? No, we don't want the other statistics. Okay, and just return. Run the regression again. Now, we only have one observation here, which is equivalent to this value here for the first growth rate. So we want both G, and we also want the estimate of the first seed value for GDP, the natural logarithm of GDP. So we run the regression again, and because it's an array output, it's going to be Control-Shift-Return. And when we pull this, so this estimate here is basically of this, and this is the estimate of the exponential growth rate. So going between 1947 to 1947.04, right? The 3-month period that it elapses, we find that actually the growth rate actually fell. That the growth rate was negative. The GDP, natural logarithm of GDP, declined in line with the GDP figure that you can see actually dropped. So we have a negative growth rate. And let's pull that down a few steps. This time the regression is for 3 periods, and the estimate of growth is for 3 periods. And likewise for 4 and 5 and so on. So let's take this all the way down, and what in fact we're actually generating here is a rolling regression. So we have a series of about half of 540, so about 260 regression coefficient estimates. If we just take the very last one here, if we double click, it's for the entire period. So it's lin-est the entire series going all the way from 1947 all the way down to 2015, and the values that we have here, copy, should correspond to the values that so if we just paste special values, we should see that they correspond. So the growth rate estimated here corresponds to the full sample estimation of the quarterly growth and the estimation of the natural logarithm of GDP. So what we have here in this worksheet is a rolling regression, and we have a series of growth estimation, right, over the entire period. But each of these estimates for growth is an ex post estimation. So this is the data available to the policymaker in real time, bar subsequent updates of data. But in terms of the trend is an ex post real time estimation of trend. Okay, so this addresses one of the issues that Orphanides has pointed out, emphasized in relation to potential pitfalls that arise when estimating reaction functions or Taylor type policy rules. Okay, so okay, what can we do with this information? Well, we could generate actual growth and compare it against the trend. So for instance, if we take this to one side, if we move this over for a moment and come back, let's estimate the trend here. Okay, so we could think of the trend, and the trend we could generate as being equal to the exponential. So let's write that in properly. Equal to the exponential of the growth rate multiplied by 4 to annualize, because it's a quarterly growth rate, and subtract away 1 so that we get an actual annualized growth rate. And we can, if we pull to the next one, you can see we're taking this level of growth, multiplying it by 4, putting it to the exponent, and then subtracting away 1. So if you like, this represents the trend, historical trend. And we drag that down. And then to estimate the actual, or what is the actual level of growth? Well, the actual level of growth could be estimated